welcome everyone. So this is, I guess this workshop was originally titled Cryptographic Attacks. And I mean, that's a fairly broad topic. So I decided, well, it wouldn't do any topic real justice if I just went over everything. So I decided to focus on a particular crypto system that, well, we covered it last week, but I want to kind of just get further in depth into it and also talk about, some classic attacks on it. And that crypto system is RSA. And so if you didn't attend last week, that's fine. I'll also give just a brief refresher on how the RSA crypto system even works. But first off, miscellaneous details. So if you want to follow along with the slides, you can just follow that link to the slides. There's the membership portal code. And also during the workshop, I'll be writing some Sage code just to demonstrate some attacks. So you can find the source code in that paste-bin link too. I just visit the slides so that you can get access to all of the links. And then finally, I think I already said this, but I'm going to be using a programming language called Sage. It's just Python basically, with slightly different syntax and just a bunch of math features. But if you know Python, then you can know Sage. It's basically just Python. And if you don't know Python, that's fine as well, because it's pretty understandable. But the thing is that if you want to download Sage onto your own computer, it's a fairly big file, just a big set of scripts, and it would take a long time. So if you don't want to do that, you can solve the challenges on the website using an online Sage REPL. So I've just linked one here called CoCalc. But yeah, if you have any trouble installing Sage or getting CoCalc to work, also just feel free to message me later after the workshop. All right, so first off, I just wanted to give a brief refresher on modular arithmetic. So typically when you talk about modular arithmetic, right, you're just talking about normal arithmetic operations like addition and multiplication, but you consider it modulo some number. And so in this case, let's say we have modulo 7. Kind of the typical analogy people give is that if you have modulo 7, just imagine you have a clock with 7 different numbers, right, 0 through 6. And if you want to compute a number modulo 7, you would basically just, the mathematical definition would just be the remainder when you divide by 7. So for example, 24 divided by 7, the remainder of that is 3. So 24 mod 7 is 3. Another way you can think about it is just if you have a clock whose hand starts at 0, you just want to rotate that hand across the clock 24 times. And so you can see how every 7 ticks, you'll end up back where you started. So it's kind of subtracting 7 until you can't subtract 7 anymore. And then what you have left over is the modulo. So again, 24, subtract 7, subtract 7, you get 21. And then what's left over is 3. And the nice thing about this modular operation is that it preserves a lot of kind of the properties from arithmetic. So for example, if you add 2 numbers, 24 plus 13, you get 37, right? And then 37 modulo 7 is 2. But at the same time, if you were to compute 24 modulo 7 first to get 3, and 13 modulo 7 to get 6, and then you add those 2 numbers together, 3 plus 6 is 9, and 9 modulo 7 is 2, again. And this is not a coincidence. It turns out it doesn't really matter whenever you apply the modulo operation. You can apply as much as you want or just at the end. It doesn't matter, you'll still end up getting the same result. And that's quite nice because it means that, we can talk about these kinds of equations as if they're just normal integers, but in reality, they're always kind of reduced under this modulo 7 operation. And the same thing applies for multiplication, right? Because it's just repeated addition. So if you have 24 times 13, you get 312, mod 7 is 4, but you could also reduce those 2 numbers and then get the same result 4 again. And so the reason why we're talking about modular arithmetic is that it's an operation that's going to be used a lot in RSA specifically, the RSA crypto system, which we'll also get into now. So what is RSA? So RSA at its core is basically a way for you to encrypt data. It's a public key crypto system, but we don't really have to worry about defining what that is. So typically, well, RSA is going to be, since it's in encryption protocol, it's going to be between two parties, and we're just going to call one party Alice and another party Bob. And besides those two people, right, there's also this kind of general public, or like the eavesdropper around your communications, that you also have to consider. And so that's kind of like the public adversary that, you know, when you're encrypting data, you don't want them to figure out what you're encrypting, right? You don't want them to learn the message. So in RSA, there are three phases, right? So the first phase is key generation. And so in this phase, basically, Alice wants to generate a set of keys. She's going to generate a public key and a private key. And in this case, the public key is going to be the product of two primes, P and Q, where the primes are randomly generated. And E is going to be a fixed value. In this case, I just have it as 3. And so N and E form the public key. And D is another value generated from the other P, Q, and E values that we don't really worry about right now, because we're not going to like talk about it for the attacks either. But that's going to be the private key. And so the point is, after key generation is done, Alice ends up with a public key, N and E, and a private key, D. And she keeps D private, but she publishes N and E, and that's kind of represented by the red arrows. And so when you publish these two values, right, you're kind of releasing it out into the open. So not only does Bob see the public key, but so does everyone else in existence, and like potentially adversaries as well. So the next phase in RSA is encryption. And so let's say Bob wants to encrypt a message and send it to Alice. What Bob is going to do is, well, he has a public key. It consists of N and E, and we're going to treat N as this modulus and E as an exponent. And what he's going to do is he's going to take the string, this message, and he's going to encode it as an integer. And this integer has to be between 0 and N, but in practice, since N is like a really big number, as long as he has a reasonably sized string, you know, he's going to be able to encode it to a number. And he's just going to take m to the power of e. It's an exponentiation, and well, exponentiation is just repeated multiplication. So it also satisfies the kinds of like nice modular arithmetic properties that we talked about before. So you can just imagine it as, you know, cubing m and then reducing it modulo n. And the result of that operation is going to be the ciphertext C. And now, once Bob has the ciphertext, he just sends it back to Alice. And again, that's kind of represented by this red arrow. And well, again, you know, it's going through parties, so it's going out into the public network. So that means everyone else, potentially adversaries, can also see this ciphertext, including Alice. And so once Alice receives the ciphertext C, she's going to perform another modular exponentiation. This time, she's going to raise C to the power of D. And if you recall, D is her private exponent. And so once she raises that to the power of D and then reduces modulo n, it turns out by some like fancy mathematics, she gets back m. And again, we're not going to worry about like the fancy mathematics. We're kind of just going to talk about the rest of how RSA works. But given this whole like suite of operations, right? We have 3 phases, 3 operations, and like they involve like, you know, multiplying numbers together, raising numbers to the power of an exponent, reducing modulo n. How come this all works? Like how come an attacker can't somehow break this crypto system? And well, they're basically 2 points of interest, right? So one is it's basically when these arrows cross over the parties and like enter the public. So one point of interest is when, well, Alice publishes her public key N and E. And you might wonder, well, is there some way to recover the private key D from those 2 values, right? It's kind of like the question, why can't an adversary calculate D themselves? Like, why can't they recover the private key from the public key alone? And it turns out, if you want to recover D, you have to be able to factor N, right? Recall that N is the product of 2 primes. And in general, we don't know of an efficient algorithm to factor a big number. And so if you're unable to factor n, you're unable to recover d, and you're unable to get the private key. So as long as factoring is hard, it's virtually impossible to recover the private key from the public key alone. Now, the second point of interest with you're like an attacker trying to break the RSA crypto system is, well, maybe you don't want to actually recover the private key, but maybe you want to be able to decrypt the message, right? Because that's the end goal. You want to be able to get a glimpse at what Bob is sending to Alice. And so one reasonable question is, well, why do you even need D to decrypt the message? Alice uses D to decrypt the message, right? But it doesn't seem necessary that you might use, like, it's plausible that there could be some other method to extract M from C. And that's kind of another assumption that we have to make, that in order to perform like this decryption, you've got to use D. That's another assumption that the RSA crypto system makes. And it kind of seems fair because we don't really see any other obvious way to perform decryption other than raising C to the power of D. And so, well, if you can't decrypt a message without the exponent D, and you can't get the exponent D without factoring the modulus n, well, why can't you factor n? Like as I said before, we don't know of an efficient algorithm, but we also don't know that it isn't possible, right? And so it turns out that, well, actually, even though we don't know of an efficient algorithm to factor numbers, we do know of an efficient algorithm that runs on a quantum computer that can factor numbers. So it kind of turns out that once quantum computers become powerful enough, RSA is kind of a broken crypto system. And so there's kind of a push, like in the cryptography community and the government, to kind of standardize new crypto systems that don't involve the hardness of factoring and rely instead on more other hard problems. But in any case, as an attacker, we don't have a quantum computer yet. So what can we do? Well, even though RSA seems like very secure in the general case, it turns out that there's a lot of kinds of mistakes that you can make that totally break the scheme. And that's what we're going to be talking about today. Like kind of different scenarios where someone might be using RSA improperly, or they just might not be following something to the exact specification. And sort of that deviance allows us to exploit the crypto system and decrypt a message. And well, we're going to, again, split it into like two different thrusts. The first thrust is going to be, well, given the public key, can we recover the private key? And recall that, like, the way you would do this is basically to factor this modulus n. So is there a way to factor n in some special cases? So the first scenario that we're going to look at is, what if we have multiple public keys and we don't know the prime factors of these public keys, but we do know that they share a factor. So for example, like if we want to write this out as a mathematical formula, we have like a modulus n1 and a modulus n2, and they're the product of two prime factors, but they also happen to share a prime factor p. And so on their own, if you only had access to one of them, well, you wouldn't be able to factor the number, right? Just because factoring is hard, presumably. But if you have both of these numbers and they share a factor, it turns out, there's an efficient algorithm to actually recover the shared factor. It's called the greatest common denominator algorithm. And if you've taken like discrete math, or, I think maybe like some high school math courses, you'll know that like there's an algorithm to basically compute the greatest shared factor between two numbers. In this case, it would be p. And well, once you get p, it's kind of trivial to factor the numbers entirely. So we're going to just briefly demonstrate this in some Sage code. So I'm going to switch to this. So this is like a Sage script that I have. These are just some helper functions. I have a function to generate random primes. I have a function to encode strings as integers, and I have a function to decode strings from integers. But we don't really have to worry about how this works. So Let's say I want to generate 3 primes. Oh, and again, this is in the pastebin, by the way, the code that I'm writing. I'm going to generate 3 primes as before shown on the slide. And the first modulus is going to be the product of 2 primes. And the second modulus is going to be the product of 2 primes as well. And notice how they both use P. And so if we were to just look at them on their own, right, they're just these big numbers. Let's say we only knew N1 and N2. And if we run this script, they're just printing out these 2 big numbers. And so on their own, again, right, we wouldn't be able to factor them. But if we know that they share a common factor, well, this algorithm is built into Sage. It's called Gcd. In Python, it's also built an algorithm into the Python math module. If you can take the greatest common denominator and you get a result, let's just call this like factor. Wait a sec. I think I'm using like a weird. Yeah, sorry. Factor equals GCD N1, comma N2. And we get this factor. We can see that it's actually the same as P. So I'm going to just run this code. Oh, wait. Sage workshop.sage. And it's going to print out the same 2 numbers. And notice how they're smaller than the moduli, right? Because it's one of the prime factors. And so given one of the factors, right, how do we decrypt the other factor? We can just divide it by the modulus, of course, right? So this should give us Q, and dividing N2 by the common factor should give us R. And we can just compare that as well. Right, so this number and this number are the same. I just printed them on the same line. This is Q. And then this number and this number, I printed them on the same line. They're also the same, and that's R. And so using the GCD algorithm, we're basically able to recover all the factorizations for both moduli. Great, okay, so this kind of, Jerry says such strong. Yeah, it's important that when you're generating RSA moduli, the numbers have to be big, right? Because if your primes are too small, then even though we don't know of an efficient algorithm, it's still possible to factorize it. So if we have like some sort of brute force algorithm, you can still factor it. So N is typically, when we're talking about real RSA keys, on the order of like 2 to the power of 1024. Like, and each prime is 2 to the power of 1512, I guess, in this case. And yeah, this seems kind of silly, right? Like, how come two RSA moduli share the same prime factors? And indeed, if you were to properly randomly generate prime factors, right, you would almost never, reuse the same prime by chance. But the real world is not like that. And a lot of the times, if your implementation is using faulty randomness, like maybe it's using a pseudo-random generator that doesn't properly seed itself, or just some other reason, just like maybe a bad implementation, this sort of attack can crop up. And there are a ton of papers about this, like about how people have just collected a bunch of RSA keys out on the internet, and they've basically conducted what's called like a batch GCD attack. And what that basically is that you try to take the GCD of all of the different possible moduli, and you just take the GCD again and again and again until you find some prime factors. And like in some instances, like close to 10% of keys that were like scrounged up on the internet actually shared the same factor, and were thus like broken. That being said, it is kind of like a weird scenario because it kind of requires your implementation to have some sort of like big fault, like not properly randomly generate numbers. Actually, okay, in the interest of time, we're going to skip this slide. This is like another type of like scenario where the sum of the prime values are known, but we're just going to move on actually to some more fun stuff. So as I talked about earlier, right, one thrust in terms of cracking RSA is being able to recover the private key from the public key, like factoring n. And the other thrust is, well, let's just ignore trying to recover the private key. Let's just try to figure out how to decrypt the message m from the value c. And remember, c is just m to the power of e, in this case, like m cubed modulo n. And I've called this roots for a reason we'll see soon. So the first scenario that we're going to talk about is, well, what if m, the message that you're trying to encode, is really small? Like maybe I want to send a message, but I don't really want to say much. I just want to say hi. And the string hi is 2 bytes. Each byte is 8 bits. So if you were to encode it as a number, it would be a 16-bit number, assuming you're just like using a standard encoding. And again, as we talked about earlier, if n is 1024 bits, that kind of far outclasses the size of m, which is a measly 16 bits. And so if m is too small, our key idea is, well, I just gave some examples here. If you have 1 cubed, that's always equal to 1. And if you take it modulo 1337, that's still 1, right? If you have 2 cubed, that's 8. 8 modulo 1337 is still 8. And the same goes, 3 cubed is 27. And again, 27 is 27 modulo 1337. And the idea is that if you take the power of these kinds of small numbers, the result isn't even big enough to wrap around the modulus. And so what happens if your power doesn't even wrap around the modulus? Well, it just behaves like a regular power. So for example, if your value m is small, then when you cube it, it's still pretty small. It never wrapped around the modulus n. And that means you could just take the cube root of your ciphertext to get m. And so this works up all the way to like m less than the cube root of n, right? And so as long as the message is actually that small, you can kind of recover the plain text trivially just by performing a cube root operation. So again, we're going to demonstrate this here. Let me clear this and I made the font a little bit bigger as well. And okay, well, let's just generate a random prime. Q is a random prime, and our modulus is the product, and E, the public exponent, is 3. Okay, and yeah, I wanted to encrypt something really small, like the string hello world, maybe. And if you print it, right, m, and you print what n is, you'll just see like the vast difference in size. So this is m, like what I've highlighted here is m, and this whole thing is n. And so if we take the power of m, right, so it would be c equals m dot power mod e comma n. This just raises m to the power of e modulo n. And this is our ciphertext. We can actually just compute the integer cube root using a built-in function in Sage called nth root e. And well, we'll get back the message, presumably. And so I'm going to decode it as bytes. And hopefully, once the decrypted result is printed, oh, it says, I forgot an argument here. Oh, something went wrong. C.nth root. Give me a sec. What went wrong? Okay, wait a second. I might have made a typo. int.2 bytes, bits over 8, big, I'll strip. Print this. Set. Okay, wait. Yeah, okay, so I think my int to bytes function wrong. It's like the decoding is somehow messing things up. But like this is a hex string, and let's just do a jank method for decoding it. Bytes.from hex. Like so. Okay, and you get hello world. I don't know why my int bytes thing is crapping out. It might be Sage being weird. But anyways, yeah, so once you decrypt it and you decode it properly, you get back the original plain text message. Okay, so again, this is kind of like, again, another contrived situation. Well, not really, right? Because, you know, maybe you do want to send small messages. But what about full-size messages, right? Like full-size messages that are up to the size of n. So another scenario is, well, maybe I want to send like a big message, right? But I'm going to send it to multiple parties. And so I'm going to take the same message, hello world or something longer, and I'm going to encrypt it to one person's public modulus and then another person's public modulus, and let's say a third person's public modulus, right? I'm kind of broadcasting the same message across to multiple public keys. And well, the key idea here is that it turns out if you have these kinds of modular equivalences, like A is equal to A1 mod M1, A is equal to A2 mod M2, dot, 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 A equals AN mod MN. This sort of modular equivalence actually uniquely defines a modular equivalence of A mod M1 times N2 times dot, dot, dot times MN. And this is known as the Chinese remainder theorem. Hopefully it makes sense. It's kind of like saying, well, if you have, like, let's just give an example. If I told you a number was 1 modulo 2 and 0 modulo 6, 0 modulo 3, then that actually uniquely defines a number modulo 6, that being 3, because there's no other odd number from 0 to 5 that modulo 3 gives you 0. But we can apply the same concept here, right? Because we have m cubed is equivalent to c modulo n1, equivalent to c2 modulo n2, and equivalent to c3 modulo n3. And so what that implies is that by the Chinese remainder theorem, well, we actually end up being able to specify m cubed modulo n1 times n2 times n3. And you'll say, okay, that doesn't seem that useful, right? We have the encrypted message, except now it's, you know, with a presumably bigger modulus. But as we saw earlier, right? Once the modulus gets too big and the ciphertext can't wrap around it, we can apply this cube root attack. And in this case, well, since m is less than each of the moduli individually, right? Then m cubed, which is just m times m, should be less than the product of the moduli, right? It's kind of like multiplying 3 inequalities together. And so if we're guaranteed that m cubed by itself is just less than n1 times n2 times n3, then again, we can just take the cube root of this m cubed and get back the original m. So this is known as Hastad's broadcast attack. And again, it basically applies whenever you send the exact same message to multiple public keys. So it's kind of like, you know, a fairly innocuous thing to do, right? You know, you just want to encrypt multiple message, like the same message to multiple people. But it turns out that this actually just totally breaks RSA, which I think is kind of cool because it doesn't seem obvious at first, but we'll demonstrate it. So, all right, let's say we have the same setup again, right? just generate the RSA key. And in this case, we're going to do a longer message so that you can't do the standard cube root attack. Like if I tried to run this, the plain text is just hello world repeated 11 times. If I tried to run this, I think Sage would give me an error saying that, yeah, the number that I tried to give it does not have a proper integer cube root. But let's say we were to instead use 3 different moduli. So E is still equal to 3, and then we're going to have an array of moduli. Right, and they're each going to be the product of separate, like, distinct primes. So we have an array of 3 moduli. E is 3, and again, this is the message, but now we're going to send a message to multiple people, right? So we're going to have an array of 3 ciphertexts, and they're going to be m dot power mod E comma n for n and n. It's just iterating over all 3 moduli and computing the ciphertext. So both n and c are 3-element arrays. We can just print them out. Okay, yeah, you can see how they're 3 arrays. And well, CRT is like a pretty common operation, so Sage also has this built in. We can compute this overall residue that I talked about on the slides earlier, just by calling the CRT built-in function. I guess I'll call it residue. And sorry, what that's going to do is, if I print it out, it's just going to be a bigger number that's cubed, or at least it should be. And so what we're going to do here is that we're going to take the cube root of this now. We'll just call it message equals residue dot. Oh my God. Okay. Nth root E, and if we print it out as a string, we get back the string hello world repeated 11 times. And so even though this was kind of like a full-size message for the RSA modulus, just because of this property or this scenario where we sent the same thing to multiple people, we're able to recover the fully sized message. Okay, so we're going to talk about one more attack. And this is called coppersmiths, and it's kind of like building on the same thing as earlier. Like, let's say I really do want to encrypt a small message, and as we saw before, I can't just encrypt it directly, right? Because if I encrypt it directly, then someone else can just take the cube root of the ciphertext because it didn't wrap around the modulus. So what we're going to do is, this is a common thing in cryptography. We're going to pad our message string to be something bigger. So it would kind of be like the string high versus the string, like a bunch of A's prepended to the string high. And so, they obviously encode the same information, assuming like the padding is known beforehand. But one of them is like a 2-character string, and other string is like a 100-character string. And so at face value, you would think, oh, this bypasses, like this prevents the cube root attack because, we can't compute the cube root anymore because it's wrapping around the modulus. But it turns out there's actually a way to break this. And it's called Coppersmith's method because it's a fairly general algorithm used in a lot of different types of cryptographic attacks besides this RSA thing. But the overall idea is that it's possible to find small roots of modular polynomials. So as we saw here, like this sort of padding, right? What the padding does is it basically, if you interpret the padded string as an integer, it's kind of like the original string interpreted as an integer plus a fixed number. And in this case, the number would be corresponding to the string a repeated. And so we can kind of rewrite our RSA equation as m plus k, which is like the overall message, then cubed modulo n, like the normal RSA encryption operation. And if the padding is known beforehand, like in this case, we always know that the padding is just a bunch of A's, then that means k is a known value. It's a constant. And m is an unknown, as well as c is a known value, right? It's a ciphertext that we as an attacker have. And so this is a polynomial, right? M plus k cubed is equal to c. If we just move over the c to the other side, we get m plus k cubed minus c equals 0. And so in particular, our message is going to be a root of this polynomial, right? Because if you evaluate that at m, then you get 0. And so what Coppersmith's method says is that as long as you have a polynomial that has a small root, you can find it. And in this case, when we say small, it works for messages less than the cube root of n, just like before. And so we're going to demonstrate this. We have e is equal to 3 again, n is equal to a prime times a prime. And our message is going to be the string hello world, except not just that, right? Because that's vulnerable to the cube root attack. So we're just going to add 100 A's to it. So now it's a big number. And well, now we're going to encrypt it by raising it to the power of e. And we get a ciphertext. So now what we're going to do is we're going to consider this integers modulo n, right? This is how you would do it in Sage. This is basically R is kind of the set of integers modulo n, and we're going to construct a modular polynomial. And this is just some more like kind of weird Sage syntax, but bear with me here. This just defines a polynomial ring. You don't have to know what that is. And in particular, this x value is going to be our like polynomial like variable. And so we're going to define a function, a polynomial that where we have m. M is basically this unknown value that we'll call x now in the polynomial, plus the padding, which is a constant. And this padding in particular is going to be, well, it's just going to be this A string times 100, right? And it's also shifted by the length of the hello world string. If you don't understand why, that's fine, right? It's just padding. There's a workshop challenge about this as well, so you can look into it more later. So it's just going to be multiplied by the bit length of hello world, which is 2 to the power of 88, right? Because hello world is 11 characters, and each character is 8 bits. So it's 88 bits in total. So we get an integer here. And then now in our polynomial, right, we raise it to the power of e, and we subtract the ciphertext c. And so if you evaluate this polynomial at m, you should get 0. Or not. Wait, let's see. I might have made a mistake. Mx plus 100 times. Oh wait, sorry. You have to evaluate it at the integer that this encodes to, right? Because at the end of the day, this is the plain text you care about. So if you evaluate it at this integer, bytes to int of hello world, then you get 0. Yeah. And so this is a root. This value here is also small. So if you apply Coppersmith's algorithm, and again, there's a nice built-in function in Sage called small roots. Sage will be able to find the root of your polynomial. In this case, it's this value. And well, we can extract it. like so. And then if we interpret it as a string, and print it, we should get back hello world. Yep. Okay, and again, this is all in the case. And so what we conclude is that even if you apply this padding to create an artificially long string, it turns out that there's still a way to extract the message as long as it's sufficiently small. And you can kind of think of Coppersmith's attack as a generalization of the cube root attack, because in the cube root attack, k is basically 0, right? It's just m cubed is equal to c modulo n. So the cube root attack involves a special kind of polynomial where you can find the small root just by taking the integer cube root. But it turns out that you can do this for any polynomial as long as the unknown is sufficiently small. And that's what Coppersmith's attack tells us. Okay, before we wrap up, I just want to briefly talk about how you would go like mitigating all of this. So the first thing, right, we talked about if you don't use proper randomness when you're generating the primes and you end up like accidentally generating a prime that's been used in another key, then you can apply the GCD algorithm to factor both of the moduli. And so the solution to this is basically you've got to use proper entropy. You got to use proper randomness, right? If you don't, then everything's like kind of screwed, basically, right? Because that's kind of what's protecting your private key from being extracted from the public key. The other thing, when we talked about the cube root attack, as well as like the broadcast attack and Coppersmith's attack, what you should be doing is you should be using randomized padding. So as you saw before here, our padding, we just prepended a bunch of A's. And that's not randomized, it's deterministic. It's a constant value that the attacker also knows. So what you have to do is instead of like prepending or padding with like known bytes, you got to pad with like random bytes, basically. And what that does is it's a twofold benefit. Like the obvious one is that it prevents you from using Coppersmith's attack, right? Because now the k value is unknown. So your overall unknown that you're working with in the polynomial is way too big for Coppersmith's method to work. The other thing is that if you do want to broadcast the same message to multiple people, if you use randomized padding, now each actual message that you encrypt to each person is different. And so now the broadcast attack doesn't apply as well. And the final thing to mitigate all of this is just to not use RSA to encrypt messages at all. And what do I mean by this? What I mean is that we should be using RSA as kind of like a part of a hybrid system where you use RSA to transmit a key and you use that key subsequently to encrypt messages using symmetric cryptography like AES, which is what we talked about last workshop. And since a key is supposed to be random data in general, it should be like robust to all the different attacks we talked about earlier, right? Because those are like particular use cases of RSA. RSA should be able to handle just encrypting randomly generated data like a key. And yeah, like the conclusion to all of this is, RSA is great. It's been around for like 40 plus years. It's still being used like up to this point, in a lot of like, your internet communications and so on. But it's very fragile. Like the moment you try to like bend it a little bit, it kind of all shatters apart. Or like, even if there isn't like an obvious way it shatters apart, like, if someone were to work on it, like a mathematician, they'd probably end up being able to figure out a way to crack your particular implementation of RSA. So the point is, don't try to do anything fancy, just use RSA as what it's meant to be. And yeah, that's about it. I'll just return to the original link slide. Again, I have like 3 different challenges on the ACM Cyber website that you can take a crack at. The workshop code is on that pastebin link, which I think would be really useful. And if you want to write Sage code, I'd recommend that website, Coca. And I'm also just happy to answer any questions either now or over like Discord messages tonight. Thank you.